Welcome to the kickoff TCIPG seminar for the new year 2013, and I hope we all had a nice break and are having a prosperous and happy new year. Today's talk is going to be given by Dr. Gabriel Weaver from Dartmouth University. He just finished his PhD. He's been a long-time associate within the TCIPG program on the Dartmouth team, and he's going to be talking about what I found out this morning. I always want to pronounce it XU tools, but I've been told that the preferred pronunciation is XU tools, and that's for Extended Unix Textual Analysis Tools. And this arises because many configurations and so on for systems that we're interested in rely on structures such as hierarchical object models. So Gabe's research has gone into the area of extensions to Unix with language constructs to make sense of these things. And this arises in the sense of making sure that your, for example, your security policy matches a particular implementation, as well as making some determinations about whether your security or what are the implications of a particular configuration change in a context-aware manner. So as I mentioned, this is the first of the 2013 public seminars. We have these the first Friday of every month. We already have them scheduled out through the spring. If you're interested, please look on the tcipg.org website. Next month will be George Arnold from NIST, which should be interesting as well. Anyway, Gabe's talk today is how extended Unix tools can measure the changing security posture of power control networks. And without any further introduction, I'll turn it over to Gabe.
Great, thanks, Al. I'm really excited to be here today. I've spent a decent amount of time with several colleagues working on this problem, which is how do we extend Unix tools to be able to handle higher level languages than traditional Unix tools can actually operate on. And there's applications in the power grid that I want to share with you today, and of course I'll try to leave time for some feedback. So it should be about 45 minutes long. So what's the big nugget picture today? The big picture nugget is that practitioners identify and categorize meaningful structures within a variety of data sources in order to evaluate security. And so what do I mean by meaningful structures? Well, meaningful structures could be things like lines, they could be interface blocks, they could be function blocks, they could be sections or subsections in a high-level policy. And we interpret many of these languages, many of these structures as languages in the language theoretic sense. And so what does that allow us to do? Well, we can apply that kind of theory to build tools to start to process and analyze text in terms of these higher level structures. And kind of the analogy here is that just as programmers use high level languages to program more efficiently, so can practitioners use high level languages to both audit and maintain computer systems more efficiently as well. And if you just look at a high-level overview of the smart grid, this is from the NIST IR report, you see a high-level interface to the smart grid is already reasonably complex, and it's going to grow more in the future. And today, it's already large. If you look at just the operations part of the smart grid, there's about 2,006 privately owned utilities, 194 investor-owned utilities. If you go to the customer side of things, there's 300 million people in the US as of 2010. That means there's about 160 million residences, and out of the 160 million residences, there's 18 million smart meters, and that's as of 2012. So you can imagine as more smart meters get deployed, we're going to have more and more computational devices on the smart grid. And furthermore, as we add more electrical cars, there's 250 million registered cars as of 2010. And as more of those become electrical, there's going to be more of a burden to be able to manage those cars as they become electrical. So substation communications at one utility involve many different devices. Remember that in the previous slide I showed you the operations part, there's 194 IOUs. Well, here's a look at one such IOU that was done in 2009. Idaho National Labs did a study, and this is one of their use cases. So one utility had 200 substations in transmission and distribution and 1 million residential customers. And so you can take each of these different sections here, these images of devices, and you can visually multiply that by 200 and visually multiply what you see in the green by 1 million. And you can imagine there's a great number of devices. And furthermore, when I was at TCIPG Industry Day, I spoke with one gentleman, excuse me, he was from California, and And he talked about there being, I believe, 500 substations and 7 million customers. And so these numbers can get quite large. And what you get as a result is all these devices need to be configured, they produce log information, and they all need to be configured in a manner that reflects a higher level security policy. And that higher level security policy could have the goal of being compliant with NERC CIP, but there's security policies and related artifacts. And many of these range from network configuration files, as you might see in Cisco iOS and Juniper. They could include Windows registries. You have substation configuration language. You have SBXML on the customer side that's starting to show up. And so you really need to be able to manage this data. And NERC CIP recognizes that. And one sense in which you manage the data is through baseline configuration development and change control. And so there's NERC CIP provisions for both of these things, which you see at the top of the slide. But the thing about these is that NERC CIP audits are important, but they consume a lot of resources. It takes about 30 man-days per day of audit. This was a conservative estimate done by a utility expert. Furthermore, audits cost large IUs from hundreds of thousands to millions of dollars, and that's just at the current scale of the smart grid. Furthermore, utilities are currently on a 3-year audit cycle, and FERC wants to increase that to annual audits. And so there's really going to be a need to reduce the cost of audit and make it more efficient. However, there's some barriers, and there's high-level research barriers that prevent cheaper and more consistent audit. And you see this in a lot of the, for example, in the roadmap to achieve energy delivery system cybersecurity, you see this. They say that we need common terms and measures specific to each energy subsector to be able to baseline security posture and operational settings, right? So we need to be able to manage this disparate data. And we need to be able to manage this disparate data and operate it in terms of multiple levels of granularity. That's a research barrier that the roadmap identifies. Furthermore, in the NIST SMART program overview in 2012, it called for new measurement methods and models to be able to measure what's going on with the smart grid. We need to be able to sense, control, and optimize the grid. And finally, when I was at the DOE Cybersecurity Information Exchange earlier in December, Samara Moore spoke a keynote at lunch and said we need cybersecurity solutions that are robust to changes in technology and be able to develop capabilities that might also be applicable elsewhere. And so these are some research barriers, research challenges that we want to try to address to make audit more affordable. And furthermore, we can view these barriers as symptoms of 3 core limitations of textual analysis. If we go all the way back to the beginning of the talk, or the nugget, where I said that practitioners analyze security policy with respect to structures. We look at those structures as languages. Well, then we can view many security audit processes and administrative processes in terms of textual analysis. So what's an example of that? Well, we just said that a wide variety of disparate data for devices exists on the power grid, but there's no real common framework to be able to handle all those different kinds of data. And so we say that that's a tools gap problem. There's a gap between the tools available to practitioners and the languages in which security policies are expressed. What's another example? Well, there's many different smart grid formats. You just saw the table earlier. SCL, Goose, SIM, SBXML, all these have hierarchical object models. And practitioners need to be able to operate on these object models at multiple levels of granularity with respect to the hierarchical model of the language. And finally, there's a discovery needs problem. In the NIST Smart Grid program overview, they said we need to be able to measure how device configurations change, and we also need to be able to understand how baseline configurations change. And practitioners really do need to measure security policy and how it evolves. We can get at that by understanding how the security primitives evolve. And so this is the outline for today. We just went through, I think it should be about a 10-minute motivation. I'm going to spend about 15 minutes on a theoretical toolbox that goes through each of those limitations of textual analysis. They're tied to barriers, high-level research barriers within the smart grid. We're then going to apply the theoretical toolbox to zoo tools, where I'll demonstrate, taking a little risk, but I want to actually show you what we have. 2 capabilities tailored to NERC CIP audit. One is baseline configuration development, and the second is change control. This should also take approximately 15 minutes. And you'll see 2 different ways to use our tools. One is the graphical user interface, and another is a command line interface. Finally, we'll briefly discuss ongoing research, and I'll conclude. And that'll be the final 5 minutes of the talk, hopefully. So let's start with the theoretical toolbox. The nugget here. We can reduce audit costs by formalizing security policy analyses. So a lot of this stuff is done manually right now. People are presented evidence. Can we formalize that to some extent? And we want to do that in particular with baseline configuration management and change control. But in order to really understand the analyses that are being done, we actually need to understand the languages that practitioners use to express security policy, and how are they actually using that language to analyze and evaluate security. And so we really need to begin with the definition of a language. But computer science has already defined what a language is in language theory. So for any kind of a language, you need a set of symbols. And we're familiar with a set of symbols called an alphabet. And we're familiar with the English alphabet. It's 26 letters. But if we also take the set of symbols to be upper and lowercase letters in the English alphabet, this is just an example of an alphabet for a language. And the language, what we can do with those symbols is we can arrange them in a left to right order and construct a sequence. And we number that sequence in left to right order because that's the direction in which we read. And we form these things called strings. So a string is just a sequence of symbols taken from some alphabet. And another example of an alphabet could be if you're dealing with DNA. We have adenine, guanine, cytosine, and tyrosine. We can represent those as a four-symbol alphabet, and we can form different strings with that, maybe codons that produce proteins. So this is something that computer science is, we encounter all the time. And so we can take these strings and start to group them. And so what is a language? A language is an unordered collection of unique strings. So in this example, we have the language of last names of people in the Baseball Hall of Fame. So we see Doubleday for Abner Doubleday. We see Cobb for Ty Cobb. We also see MacPhail. MacPhail could correspond to, I believe it's Lee or Larry MacPhail. They're the only father-son combo in the Baseball Hall of Fame. However, there's only one entry in that set because we want an unordered collection of unique strings. So that's what a language is. And the next question we want to be able to understand is, well, given a string, is the string in the language or not? So, for example, I throw a string Cobb as input, and I have this little computational engine called a recognizer, and it returns true if the string is in the language and false if it is not. And so what this gives us is a way to start to formalize the tools gap problem, which, remember, we have a wide variety of disparate data, and we want to be able to have a way to operate on this data in a uniform way, even though there's many differences in the models that they encode. And so language theory categorizes languages into different classes based upon how difficult it is to say whether or not a string is in the language. And we do this with recognizers. And so one kind of recognizer is the finite automaton. And we give it an input string, and it has some states, and it returns true or false, whether or not that string is in the output. And if that is the kind of recognizer we need to recognize to say whether the string's in the language or not, we call it a regular language. So this is a class. It's a set of languages, and languages are sets of strings. Let's say we want to be able to, I give you a string, and you want to be able to see whether it has properly formed or properly nested parentheses. You can't do that with a finite automaton. The parentheses matching problem requires us to go to something called a push-down automaton, in which we add a stack, and now we're able to see how deep in a hierarchy of parentheses we are, or any hierarchical object model. And we call these things context-free languages if they can be recognized via a push-down automaton. And so language theory gives us a framework to understand the tools gap problem because a lot of the languages that use hierarchical object models that we encounter in the smart grid aren't regular. But regular languages have some nice benefits because they have all these Unix text processing tools built for them. So we can do things like compare, extract, and count the contents of files relative to a regular language. But we can't do that for non-regular languages. There's certainly tools out there to start to compare things like sim, to patch C in terms of its structure, and to grep and compare XML. But there's nothing really out there that allows us to, in general, operate on a context-free languages with the generality that Unix text processing tools provide. So parsing and the granularity of reference problem. This is the granularity of reference problem, remember, says we have these hierarchical object models. We want to be able to operate on them at different levels of abstraction. And so to do this, we can start to use something called a parse tree. And I'm going to briefly run through this. So what is parsing? I give you an input string, and I have this thing called a parser for some grammar, which I'll explain in a bit, but it's a way to specify a language. And the parser will produce a thing called a parse tree if the string is in the language of the grammar. And so, for example, I have input string of called cob, or the string cob. I put it into the parser, and I start with the start symbol. And within the grammar, you see that there's 3 different rows. Each of those we call a production. On the left-hand side is a thing called a non-terminal, and we can substitute non-terminals with whatever's on the right-hand side. So we start with the start production S, and we can expand it into the terminal, the character C, uppercase O, uppercase B. And we notice that the terminal C matches the first character, the first symbol in the input. So we can move on. Now our input reader is on O. We go to the non-terminal O. We expand that by the production rule, and we match. And we continue this process until, if the string's in the language, we can actually produce a parse tree. And the parse tree, in some sense, gives us an insight into the different levels of abstraction that are represented by that string. So what's an example of that? Let's take a natural language security policy. This could just as easily be a NERC-CIP natural language document. But if analysts are used to analyzing in terms of sections, subsections, the kind of structures you might see in a legal document. These are structures that people use to evaluate security. And so if they want to evaluate relative to sections, we can produce a parse tree, and we can look at all of the subtrees whose root is produced by a production corresponding to sections. And we can grab the strings that correspond to those subtrees, and we can start to think about it as a language. And I'll talk about that more in a bit. If we continue looking at the parse tree in more depth, however, maybe I'm interested in just looking at the subsections. And so I can grab all the strings that correspond to subtrees of type subsection, whose roots are, whose strings correspond to subsections, and I can operate on that. And I can continue this paradigm. So what parse trees do is they give us a nice formalism to start to think about multiple levels of granularity, and that allows us to then operate on languages. And discrete mathematics can allow us to do that. They can allow us to start to measure security in terms of security primitives represented within text. So we can use this thing called a data type. So a data type is just a set paired with operations on elements in that set. And we want to think about sets of security primitives, things like sets of roles in a network configuration, or sets of sections and subsections in a high-level security policy document. And we compare that language up with some operations, things like equality and distance and parsing. And now we can start to maybe formalize textual analysis a bit. And so one notion is distance, one operation is distance. And if we're in a context-free language, remember, we can not only compare elements in the language in terms of their sequence order, the sequence of their symbols, which is string at a distance. We can also compare it in terms of the structure that string represents relative to some grammar. So we can start to look at the tree at a distance as well. And furthermore, depending upon the language we choose to do the security analysis with, we may be able to actually get trends in how different security primitives evolve through time. A quick example, sections have identifiers, like section 1 could be the introduction, or an interface may be identified by a unique string. And because we're using meaningful sections, meaningful blocks of text that have these identifiers, we can compare how these things change through time. You can't do that with lines. The language of lines is much more volatile across multiple versions of a text. So you can actually start to get trends. So those are the 3 kinds of tricks or tools we can use from computer science. We can use language theory, parsing, some stuff from discrete mathematics to address the different high-level research barriers to a more efficient audit and to help administrators evaluate security, thus saving cost. Now I'm going to talk about some ZooTools capabilities. This is where the talk gets a little bit interesting for me because I'm going to do some demonstrations, and it's always fun to try to do demonstrations on the fly. But the 2 capabilities that I'll discuss today are baseline configuration management as well as change control. And so what we're going to do, we're going to take the theoretical tools that we talked about earlier, we're going to apply them to address the core limitations of textual analysis, the tools gap, the granularity of reference problem, the policy discovery needs problem. And we're going to show how, as a result, power control network security audit can become more consistent and efficient and hopefully save money as well, as more audits are in demand. So just a quick refresher, traditional Unix tools operate on regular languages, but those don't recognize arbitrary hierarchical structure, and that's the kind of structure you encounter in object models that you see increasingly in the smart grid. And so what we did was we built extended Unix tools, ZU tools, or XU tools, depending on your preference, to operate on languages with arbitrary hierarchical structure. And so the three tools that we developed was one corresponding to diff, which allows us to compare, one corresponding to grep, which allows us to extract, and one for WC, which allows us to count structures, high-level structures within text that express some notion of security policy. So capabilities for baseline configuration. Two capabilities I want to talk about today, and I really want to get feedback from people on these capabilities. So one is we need to be able to inventory security primitives, and two is it's good to have an inventory for baseline configuration, but we also want to be able to identify important security primitives where important should be in italics. We define that notion of importance. So what are some use cases for baseline configuration? Well, there's two that I'm going to talk about today. Both of these appeared in our 2012 PECI paper. For network configuration, an example might be, maybe I want an inventory of roles, which are groupings of users, devices, and protocols defined in an access control policy for a network. Now, maybe I'm not going to get into what exactly an access control policy for a network is, but suffice it to say, roles make it easier to express rules in a security policy. And so I want to be able to inventory those roles that are used. For Windows machines, we want to be, and why do we want to do, why do we even want to have an inventory of roles? Well, because there's study in network configuration management that showed more roles make firewalls harder to manage. And so if we can see how many roles there are per firewall or per network device, we can start to get insight into maybe where we need some refactoring or where, as an auditor, you should look for complexity. Windows machines. A lot of machines on the power grid are Windows machines. This is from a utility expert. And so it makes sense to start to think about using the Windows registry as a representation of a baseline configuration. And what's the current state of the practice in terms of this, in terms of cataloging the roles, in terms of identifying the most important interfaces or roles? Well, there's really not many tools available to help practitioners in the realm of baseline configuration. Many utilities use spreadsheets to manually document baseline configurations of systems, but that's not going to scale as the number of devices increases over time. You can't really work with that data other than visually. Maybe you can process it, but we will make that easier. Also, manual documentation is error-prone, inconsistent, and it doesn't scale. And maybe this sounds a bit harsh, but if we looked in some of our previous work, if you look at software engineering, code and comments don't co-evolve. People generally don't like writing documentation. And furthermore, that documentation may not be relevant several months down the line to an auditor. An auditor may be interested in a different set of security primitives than those which were documented. So if we can, maybe there's a better approach, or at least another approach that's complementary. So today I want to give a little demonstration with an artificial but realistic data set. For those of you that were at TCIPG Industry Day, this may look a little bit familiar, but I've actually extended it a bit. And this is also an example of a graphical user interface to our tools. So you don't have to be, the goal there is you don't have to be a command line interface wizard in order to use our tools. It should be intuitive, and that's something we strive for. So here you see 5 firewalls on a network that's representative of what you might see at a IOU. I don't want to show you that yet. So let's begin. First thing I want to do is load the configuration files into this little viewer. So what you get with a tool like NetAPT is a really nice high-level view of the topology of a power control network. But we want to be able to process security primitives at multiple levels of granularity, right? That was one of the research challenges. So you want to be able to process these configuration files with respect to the hierarchical object model of Cisco IOS. And so the first thing we can do is just load the configurations in, and it's a language where each element corresponds to the contents of a configuration file. And we can see that language visually here, where each string in that language corresponds to one of the orange circles, and we have 5 as we saw in the picture before. Now I want to be able to work at another level of granularity. I want to be able to extract, let's say, the roles within each configuration file, and so I use zogrep for that. So zogrep will then produce a set of roles. So this is a language whose elements correspond to strings that represent roles in Cisco iOS, and immediately we can see which firewalls have the most roles or fewest roles defined. For example, the internet firewall only has 2 roles defined, whereas some of these others, I think this is primary EMS, it is, has many more roles defined. We also can get a little more adventurous and extract interfaces, right? So that what we did there initially was we analyzed the configuration files with respect to the language of roles, those security primitives. Now maybe I'm interested in looking at the firewalls with respect to the language of interfaces. So let's do that. And we just drag the interfaces down into the set view, and we can see quite a different view now, where before we just had the internet firewall with 2 roles. We see that these are all pretty homogeneous. Furthermore, we can now start to think about the size. So that was the inventorying, right? And we could start to inventory things like roles and interfaces and other security primitives. Now we want to be able to identify important security primitives. One notion of importance could be the number of lines used to specify these different primitives. Another notion of importance could be the number of IPs to which a certain security policy rule applies. So today I'm just going to show you the lines. We have roles. We're going to count the number of lines per role and put it in something called role sizes. And we drag that down right here. And I can immediately see that the business lines role has significantly more lines to it than something, let's say, like the EMS servers role does. And I can do the same thing for interfaces. But the idea is to give an auditor or an administrator a quick way to dive down, to drill down, and analyze these configurations with respect to different languages, with respect to different security primitives. And so how do we do this? Well, we have this design for ZooWC. It corresponds to a command line interface. And so what you saw visually, I'm just going to show you quickly now. And it looks like I'm doing okay for time, so I can relax a bit. What ZooWC does is what I just showed you. So maybe I want to count the number of interfaces per router configuration file. So I have router.v1.example is my input, and I want to be able to just count the number of interfaces within that. Now that's an improvement over traditional word count, because traditional word count you can only count lines, words, characters, and bytes. So now we're going to count higher level structures within the file, and I can do that, and I see that I have 2 interfaces in this example, so 2 interfaces total. Maybe I'm interested though in not counting the number of interfaces relative to a file. Maybe I'm more interested in actually counting the number of lines per interface. And this is what you saw graphically, but this is the command line version. And so what I can do here is I say there's 7 lines within the loopback 0 interface. There's 9 lines within the gigabit Ethernet 4.2 interface. There's 16 lines over 2 interfaces total. So this starts to let me see within each of my router configuration what normal looks like. What are the outliers in terms of importance or complexity of specifying these different high-level structures. So that's what I really want to talk to you about. So here you have the interface. We say it's ZooWC. Given these 2 input files, I want to be able to extract all the interfaces. And we can represent that as this thing called a ZooPath query tree. So what this means is at the beginning of the querying process, we have the root of the tree. We give it 2 input files, router v1 iOS on the left, router 2 v2 iOS on the right, and we extract the interfaces. And ZooWC says, oh, there's 2 interfaces in the subtree corresponding to router v1 iOS, and there's 2 interfaces for router version 2 as well. So, and we can also do things like count the number of lines per interface. You just saw that. But what we did in the last step was say, I don't want to just count in the context of a file. I want to count relative to other higher level structures. I want to be able to process data at multiple levels of data granularity. And so what I can do is use the context flag to say, extract the number of lines per interface and give me the counts in terms of interfaces. So I can see there's 7 lines in router V1 loopback 0 interface. I can see that there's 9 lines in router V2 gigabit Ethernet interface. And so that's really the first capability. So what can we do to baseline security posture as it's represented by network configuration files, but it's really not limited to that. Our tools are designed to act more broadly on a broad class of context-free languages, and those are what we see in data formats that are increasingly used in the smart grid. Now I want to talk to you about capabilities for change control. This also came up at TCIPG Industry Day when I was talking to utilities. They're also very interested in what are some things we can do for change control. And so the 2 things I'll show you one today, but I want to have you keep 2 things in mind. One is change log generation. I'm going to go over for use cases for that in a bit, but change logs take time. It's like documentation. It can be unreliable. It can be inconsistent. And we also want to be able to measure trends. So currently we're able to compare files pairwise, but what does it look like over time? How do we know when a significant change has been made? What's normal look like? And so use cases are the same. For network configuration, I want to be able to compare network configuration files in terms of high-level language constructs rather than just lines, right? So if I have, I'm an administrator and I delete an interface that is 8 lines in length, and then I add an interface that's 8 lines in length, should I express that change log in terms of lines, 8 deletions and 8 insertions, or should I express it in terms of a deletion and an insertion relative to the interface structure? And my opinion is that you should allow the user to choose. What do we want? How do we want to summarize the data? Windows machines as well. There's a need to be able to compare baseline configuration to that which is actually on machines in use, and so we can do that using our tool, and that's important. I'll focus on network devices though. We want to be able to summarize how devices have changed over time relative to hierarchical network configuration model. We also want to be able to view trends in how the network has changed. And the current approaches, I'll show you in a bit, there's this tool called Rancid that gives practitioners a line level view of changes between consecutive versions of configuration files. It uses diff to be able to give us a summary of what changes were made, and it emails the administrators what changed. I'll show you that in a bit. Change Gear and Remedy don't actually extract changes or summarize changes directly from the configuration files, but they are ticketing systems, and they allow people to document changes. But this could be error prone, and it may not necessarily capture the information in which an auditor is interested. And Splunk and search-based approaches. This was from Himanshu when we presented this at Industry Day. He's like, what about Splunk? So I looked at Splunk, and they don't use context-free languages. They rely upon regular expressions to identify key value pairs. So we take a different approach, a more language theoretic approach. And so I want to show you today is a quick demonstration of change logs at different levels of abstraction via ZooDiff. And just so there's nothing up my sleeve, you'll see the two versions of the example file I give you. It has 2 interfaces defined. On the IP address line, we changed the IP from 185 to 581 from between versions V1 and V2. We changed the name of the crypto map from Azalea to Daffodil. We delete the IP access group inbound filter out line in gigabit Ethernet 4.2, and we insert the IP flow ingress line. So if the tools are working correctly, you should see some indication that those are the changes that occurred. So let's start. Okay. So first I'm going to show you traditional diff. For those of you not familiar with diff, you give it 2 input files, and these are the input files I just showed you, and it gives you line level changes between the 2. So this is what Rancid uses to report changes to administrators. And you can see that, yes, indeed, the IP address line was deleted and then inserted, so it was updated right where I said it, right where I showed you the data would be. And crypto map Azalea got changed to Daffodil. You see the minus sign for deletion, the plus for insertion. And the inbound filter outline for interface gigabit Ethernet 4.2, that was deleted, and IP flow ingress was inserted. So it's good for line level changes. But if I'm interested in seeing how the configuration file as a whole changed, and here I'm going to use zoodiff. So what zoodiff does is it parses the contents of each of those example files, forms parse trees, and uses a tree edit distance to see how far apart those are. And distance in this notion is not in terms of lines, but in terms of nodes on the parse tree. So it costs 1 to insert, delete, or update a node within that parse tree. And so what I'm going to do is find my cursor and use zoodiff. And so what I can see, I'll move this up, is that I have an update between the two versions of the files, and in total a cost of 4 was incurred on the whole parse tree. And now I'm gonna go here. And so I'm gonna use zoodiff again, but this time I'm gonna look at how the interface has changed. And if we scroll up, here's what the example we're actually drilling down into the hierarchical object model of Cisco IOS. We're able to see that there were 2 nodes changed in the loopback 0 interface and 2 nodes changed within the gigabit Ethernet 4.2 interface as well. Maybe I'm actually interested in the whole enchilada. So now we can see all the changes, right? So here within loopback 0, we see that this IP address line was updated and it cost 1, and so the total cost was 1. We see that azalea was changed to daffodil, so that line was updated, that cost 1, that's why there's a U there. We see a deletion within gigabit Ethernet 4.2 of this line, so that incurred a penalty of 1. And we also have an insertion of the IP flow ingress line. And so we can start to see not just costs, but costs aggregated with respect to the structure of the document. But some people may say, well, it's really not necessarily the cost I'm interested in, because it costs just as much to change an IP as it does to delete an entire line. That really doesn't make sense. So one thing that we also do is we allow people to specify their own cost functions. So we can use a word cost function now. And so what we can see here is a much different picture from what we saw before. So if you look at the top of the screen, actually if you look at right down here, you'll see that there are 2 word level changes. 2 words were updated in loopback 0, right? The IP address and the azalea went to daffodil. Whereas in gigabit Ethernet 4.2, there were 7 changes. Now we were looking at the cost in terms of operations on parse tree nodes. It looked like they both had the same amount of change. But because we're able to specify costs with respect to different structures of the text, we can really start to look at the kinds, analyze with respect to different cost functions as well. And now another neat thing I want to show you is maybe I'm interested in character edit distance cost. And I want to be able to see very slight changes between the 2 versions of the configuration file. So I can actually pipeline the output into awk and say, give me all changes that are more than 0 characters long, right? But less than 5 characters long. So I can see really small changes. And I use that, and that allows me to see that, yes, the 185 was changed to a 581. So three characters were, 2 characters were changed there. And that's a very slight configuration change. So that's what I wanted to show you for zoodiff. How does it work? Well, zoodiff doesn't actually, so we have a data type. A data type consists of a language, right, which is a set of strings and some operations. Well, we can parse the strings in that language and then do a tree edit distance. And that's exactly what we do. And this example reflects what we just saw, where the loopback 0 interface was updated and the gigabit Ethernet 4.2 interface had a deletion shown in red and an insertion shown in blue. And what's the magic behind it? Well, we use the Zhang and Shashik tree edit distance algorithm. And it's a really pretty algorithm. If you just consider a tree that represents a string, it falls into the string edit distance problem quite nicely. So it's really a beautiful one, I think. And so that's what I wanted to show you today, were the ZooTools capabilities for baseline configuration development as well as for change control. Now I'm going to talk to you for about 5 minutes on ongoing research, and then I'll conclude. So it looks like I'll be 42 minutes long, not too bad. So project activity in December 2012. This is I believe it's managing or usable management tools for humans for the smart grid data avalanche. That one, that's the project I'm talking about. We were pretty busy in December 2012. We went down to DC for the Smart Grid Cybersecurity Information Exchange, and we got some really good feedback, both in terms of barriers for audit and what kind of, right, I was talking about the keynote by Samara where she wants technologies that can handle evolution in technology. And how do we address that? Well, this ZooTools is saying, let's base audits. We can still start to semi-automate audits, but we can do so relative to a higher level language that persists across technology. So things like network interfaces, they exist across Juniper and Cisco devices. Things like roles aren't going anywhere in terms of access control policies. So if we can operate on a higher level than the actual encoding of these structures, then maybe we have a chance. And the next week, we went to Unix Lisa, where we didn't speak to the power grid crowd. We actually spoke to network administrators, system administrators about our tools. And we got many different questions from a number of companies. Questions went on quite a bit. And then I did the PhD thesis defense. And then on Christmas Eve, it was kind of a cool Christmas Eve because the ZooTools user group, we have a user group if you're interested in contributing. We got our first contribution. A gentleman named Igor needed to use our tools for his work. So he actually started writing a Juniper parser, and we're working with him. So that really shows one of the benefits of open source is that people will pick these tools up and start taking them in directions, and you can maybe snowball. So that could be interesting in the future. So I just want to conclude very briefly. The kind of take-home nugget is our ZooTools operate in hierarchical object models, and we encounter these models in the smart grid increasingly. And so there's many different possible future directions for ZooTools, right? But already our current ZooTools capabilities, which I showed you today, I argue they're useful for both auditor and administrator. And how so? Well, we talked about baseline configuration development. We also talked about change control. What were the capabilities? Well, for baseline configuration, we'll be able to inventory security primitives and identify important security primitives, right? So I showed you that graphical user interface view of ZooTools. And that can address baseline configuration development for NERC SIP. It can also allow us to maybe secure and validate field device settings, one of the NIST-IR vulnerabilities. For change control, I talked about changelog generation, right? Writing documentation is time consuming, it may not stay relevant. So if we can actually generate changelogs directly from these different files, this different disparate data at multiple levels of granularity, maybe we can make sense of it. Maybe we can start to easily update network documentation within 30 days of a change, no problem. Maybe we can, in terms of change trends, start to understand, like, when did a major trend occur? And if I'm an auditor, zoom in on that time period. What happened there? Is that normal? Was that documented? And finally, for vulnerabilities, we can address inadequate change and configuration management and inadequate periodic security audits. If we make these tools usable enough, it even opens up the possibility for self-audit. So as audits become more frequent, people can just do self-audits as well. It's one idea. I'm not an auditor, I'm just throwing that out there for discussion. But I just want to say thank you, and I'll take any questions. That's the website for the tools, and we have a mailing list. But please email me if you have any questions, and I'm ready for questions now.
Thank you, Gabe, for a great presentation. So since you had a contribution on New Year's Eve of a new language parser, and you showed the use of the Cisco iOS parser, you didn't mention what it takes to actually create a new parser for something. So for the audience benefit, can you explain what is involved in adding a parser for something new that your tool doesn't currently understand, and
Sure.
what's involved in that?
Yeah, so this is actually a question I need to document better because I get it a fair amount. First of all, I have an interface for grammars and parsers. And so the current way in which we implement grammars and parsers is through the PyParsing library. It's a Python library that allows us to use function combinators to start to parse these things. So really what you need is a production for every structure, or maybe you need productions for the structures in which you're interested in parsing, And it doesn't have to be the entire language. For example, Cisco iOS is a context-sensitive language. That was out of AT&T research, right? And then they said, well, you can have a meaningful subset that's context-free. And so that's what we use for our grammar. Igor, when he built the Juniper OS parser, he had in mind the structures in which he was interested in, and then he used the Parsing library to write those parsers for those structures in particular. And so the thing about ZooTools, one of the meta arguments I'd make is that you don't have to specify the entire language, and you can specify the meaningful subparts of the language in which you're interested in. And furthermore, those meaningful sub-languages that get used could be specific to an organization. They don't even have to be at the programming language level, which could be really neat for developing specific vocabulary for, let me go back. There's a bullet I really want to hit here. It's basically the barriers right here. So we want to be able to have common terms and measures specific to each energy subsector, right? And so if you can specify a language that maybe not a standard language, but for a specific subsector, I think that could be really powerful as well. But the current effort is you know the structures you want to extract, you use Parsing to specify that language.
Okay, we have a question from online here. Jason Holcomb asks, have you looked at integrating other SCADA security baselines such as Bandolier for OS and application configuration?
No, but that's great. Yeah. Did you save these questions, by the way?
Yeah, I can.
Great, thanks.
Hey, I'm Edmund Rogers. I work here at the University of Illinois. What's the status of the project now that you've graduated?
Right, so now that I've graduated, it's an open source project. It's licensed under the GPL v3, and so you're free to work on it, and I'll be maintaining it periodically. Yeah.
Another question for you, and this is Tim Yardley, University of Illinois.
Okay.
Obviously, this was presented at Unix Lisa as well, and that's a non-Power Grid audience. This has been presented in the Power Grid domain for this case, but you've shown it with static configuration, and I know since this was TCIPG work, I'm privy to more information than what's been presented here, but this has also been discussed in the use in dynamic context where information may be streamed into it or used in other ways, right. Where it's operating on perhaps, say, even a real-time basis. Yeah. The tool itself has a lot of potential opportunities, just like the Unix tools can be piped information and continue to operate that. Have any of the user group or other avenues like Unix Lisa brought up or explored any of those other avenues of use yet?
Yeah, so one of the questions that, well, it's kind of related. At TCIPG Industry Day, so we want to be able to start to process things on the fly, right? Well, on a slightly different note, at TCIPG Industry Day, I believe it was one of the practitioners from Honeywell said, have you thought about very, very large data sets and how you can maybe do that in parallel? And what's nice about our WC and grep is, yes, we can do that in parallel. Now, diff is a little bit trickier, right? But luckily, the Zhang-Shasha algorithm can also be parallelized. So there's hope to, not from the user group, but from actually the Power Grid community. Honeywell, I think, was interested in how well do these things scale on larger data. Now, to be able to parse in parallel, there's also literature I need to look at to explore that avenue. And in terms of broader impact, you could use this in any number of things. Right? This third bullet on this slide is actually really relevant. We need cybersecurity solutions that are robust exchanges of technology, so I say use a high-level language, and develop capabilities that might be applicable elsewhere. I mean, you could apply this to natural language documents, not just security policies. You can apply this to source code. If I threw this on coupled ZooDiff with a version control system, you could imagine being able to get some really interesting trends, development trends as well for source code metrics. Those are all areas, if I pursued it, to do a lit review on, but I think there's a lot of broader impact as well. So.
So you mentioned applications to Windows Registry, and a lot of your examples were around Cisco iOS. And of course, you did point out that these are very widely seen in power systems.
Yes.
I was wondering if you had anything that would be more power system specific, such as either SCL or Goose, any use examples in that area?
Yeah, so one thing I was talking about in the meetings this morning with Tim was thinking about, so for the test bed and for substation automation, could you actually start to compute a communications interface on the fly? So these different devices, these IEDs have configuration, they have capabilities that are expressed in XML. And by using that notion of corpus as a data type, you can define notions of equality, so one or two structures equivalent. Furthermore, there's some work that I think it's out of EPRI, which was mapping between DMP v3 and 61850. Again, if you define, you can think about that as two different languages that are expressing similar concepts, much like Cisco iOS and Juniper. And then you can define your notion of equality on that language, because it's a data type that respects that mapping. And so I think there are a lot of interesting things, both in terms of communications interfaces for substations, as well as setting up experiments within the test bed as well for managing those configurations.
I just can't stay away from the mic.
No, I'm enjoying
So something you said triggered a thought, which I don't know if
Could be
this
dangerous,
is something that would actually be possible or not, but it might be. So one thing that happens with code source auditing is in some cases you look for patterns in say a C application, like you may just grep for sprintf, for instance, if you're looking for string vulnerabilities.
Sure.
So this is a two-part question. You mentioned tying into source control systems. So have you looked at the capability of using like a standard parser like a Lex or Yak parser for say C to tie into this, so you don't have to write a parser for dealing with like say a C application? And then the second part of that is, if you could say parse a C application and understand the context of the C application, could you do something more intelligent to look for things like buffer overflows and string format exceptions using your tool by saying, okay, here are examples, knowing the grammatical structure of what a buffer overflow looks like in context. Here's examples of that, and look for similarity to these in applications and find those.
So there's a lot of fun. I got to serialize this. It's like a graph in my head right now. So first, for a standard parser, that was something the thesis committee also was asking about. And so the way I have the design in the thesis currently is it's an abstracted module where you say get the parser, get the production, and it returns you the corresponding string or the token that you want. So you could have actually a standard C parser. But I haven't done any more legwork than make it modular so that it could be included. If I could do that, so C application, could you then take a big application and start to understand security vulnerabilities? Is that your question? Good. I'd say yeah, and that's kind of a second order service to ZooTools, right? Because ZooTools really focuses on parse trees, which is syntactic, right? And then if you're looking at semantics, there's a whole nother wonderland I could play with, where I could pair up semantics associated with things like buffer overflows with the syntactic structure of the parse tree. So it can start to pull from programming languages again and parsing. And yeah, so I think that's a really interesting area.
Let's thank the speaker again.
Thanks for having
me. Welcome to the Illinois team. I'm sorry, that Gabe will be joining the Illinois team in a couple of weeks. And also some of this work has received publicity in the computer science press. It's been written up in Computer World, Communications of the ACM, and CIO Magazine, and was also slashdotted, which is sort of our equivalent of getting on the cover of Rolling Stone. So Gabe is to be congratulated. Pete, did you have anything? Okay, all right.